Hello everyone, welcome back to Exploring Quantum Physics. I'm Charles Clark, and in this lecture we're going to explore the physics of gauge potentials, spin, and magnetism. These are foundational topics of quantum physics, still very active subject of discovery and research.
So let's start with a basic introduction to the idea of a gauge potential, and in particular its application to the most familiar form of the gauge potential, which is a magnetic field. Now, up to this point in this course, the sorts of Schrodinger equations that we've dealt with will usually take this form. They have a kinetic and a potential energy part. And the potential energy, it comes to us basically from analogies with classical mechanics. The potential energy is a function, the derivative of which gives the classical force. So you see, the potential energy is defined by a first-order differential equation, and that leaves its specific value undetermined, in that it defines the rate of change of a potential, but doesn't necessarily specify what the absolute value of the potential is. Is that a feature or a bug? Now, in phrasing the question put to you in that previous quiz, I emphasized that changing the potential by a constant value is physically feasible. For example, take the experiment upstairs. You're in a different gravitational potential, and so if you're talking about, say, the bouncing ball problem, and you're bouncing on the higher floor, then your natural reference point is at a different position than it was before you took it upstairs. And so, well, I guess we just better look and see what has to be done in order to describe the same system from two different reference points. Or to put it another way, how do we relate the solution of the Schrodinger equation with one choice of the origin of the potential with respect to another choice? So I hope that you saw from thinking about that example, the previous quiz, that if you change the potential by adding an arbitrary constant to it, then the wave function acquires an overall time-dependent phase. Now, such a phase is not observable in itself because every time we take an expectation value, it cancels out. And indeed, it's never really possible to identify the overall phase of any wave function. But effects of this type are used in certain forms of interferometry. For example, here's a classic cow experiment by Colella, Overhauser, and Werner, first demonstration of neutron interferometry to show the effect of gravity on a quantum particle. A beam of neutrons is sent in, it's split, goes through beam splitters, and then recombines, interferes in the output ports. And the angle of the interferometer is varied so that this path here is higher in the gravitational field than the other path. So when you split the beam and put part of it uphill, it acquires this faster time-varying phase, and then when recombined, you can see the effect of that phase shift. So now we're going to turn to an even more uncertain definition of potentials. That's encountered in the theory of magnetism. Now, we're necessarily using results from classical electrodynamics here, and they may not be familiar to you. They're very standard and can be found in any textbook on the subject if you haven't had a course in it. But here is how, in Maxwell's equations, a time-independent magnetic field is specified. And this is the case that we're going to treat during this lecture. So the magnetic field B is given by the curl of a vector potential, and then the measurable magnetic field B determines the motion of a charged particle, a particle with electrical charge Q and mass m, by means of this so-called Lorentz equation. So the acceleration, the force on the particle, is equal to the cross product of the velocity and the magnetic field. So in contrast, the force that's due to an ordinary potential, such as gravity, doesn't depend upon the velocity. It typically just depends upon the position. So these are very different types of phenomena. Now, furthermore, we can ask the same question about the vector potential as we did about the scalar potential, and the result is richer and more interesting. So if we have a vector potential that gives the magnetic field B, then we can add the gradient of any arbitrary function to it and still get a vector potential that satisfies the same defining equation for the measurable field. So in practice, one has to choose a specific value of the vector potential, and such a choice is called a choice of gauge. And now you are going to be given the opportunity to choose a gauge. Okay, now, how do we describe the interaction of a particle with a magnetic field in quantum mechanics? I don't have the time to derive this prescription for you, but it comes from the way quantum mechanics is generated from the Hamiltonian form of classical mechanics. Actually, it's the same procedure that's used in classical mechanics. It's just that you replace the classical momentum by the operator when you go to quantum mechanics. And so this is how it's done in quantum mechanics. If you have a Hamiltonian, let's say you have a Hamiltonian in a system where no magnetic field is present, then you turn on a magnetic field. The way that you account for the presence of the magnetic field is to replace in the Hamiltonian every occurrence of the momentum by the momentum minus Q over C times the vector potential. We're going to discuss this simplest possible case, which is the Hamiltonian for a charged particle. No other fields present, but in the presence of a magnetic field. Lots of things change when you do this minimal substitution. So for one thing, you find that the velocity operator, which describes the time derivative of the position, is now given by this form. And so it's no longer just the momentum divided by the mass, which would be the case in the absence of a magnetic field. Moreover, I think you want to pause before going to the next part and carry out this calculation. It's very straightforward. And what it shows you is that, in general, the different Cartesian components of the velocity operator do not commute. Now, this is very much different from the case when no magnetic field is present, because then the velocity is just proportional to the momentum, and the components of the momentum operator do commute. So the magnetic field introduces something quite unusual. And another point to be made is that when you look at this commutator, which is really, when you think about it, it's the way that we approach most of the quantum problems. The commutator no longer involves the gauge, but only the measurable magnetic field. And we're going to exploit that fact later. Now, I like writing it in this form, that commutation relationship. The cross product of the velocity with itself is an imaginary number times a constant times a magnetic field. We'll use this, and then here is an alternative way of writing the Hamiltonian. It's just 1/2 mv squared. Well, you see, that looks like the kinetic energy of a free particle. So it's as if there's no presence of the magnetic field in that sense, except there is this hidden, subtle presence associated with the commutation relationship. But this is an indication that of something we'll soon see in the next part, that the energy is just a form of kinetic energy.